Hello everyone and welcome. My name is Fadi Salama and I would like to present to you our paper A-Mage, Atomic Mashup Generation for the Web of Things. I will start right away with the motivation behind this paper. So let's imagine a smart home scenario in which multiple devices have to interact together to perform a specific functionality. For example, we have here a motion sensor, a smart light bulb, a smart coffee machine, and a smart curtain, all working in tandem to perform a specific functionality. We also have a mashup controller in between that regulates the communication between all these devices. For a mashup designer that wants to use all these devices, he needs to know the interactions or the functionalities that these devices expose, as well as the network interfacing of each device to actually know if they can actually communicate together. To ease this and to facilitate an easier discovery of devices, the W3C proposed the thing description standard called TD in short, and the thing description is just an LD document that is both human and machine readable and describes the interactions that an entity in the web of things can expose, as well as its networks interfacing. And they are grouped in properties, which are the states that the device exposes, actions, which are physical actions that can be invoked, and events, which are notifications that can be emitted from the device. This alone, however, is not enough to describe a whole system, and therefore an extension was proposed called the system description, and the system description is the same JSON-LD document with extended keywords, and it allows the description of mashups using small building blocks called atomic mashups. And the atomic mashups have always the same structure. They are small mashups that cannot be divided further and perform a specific functionality, and their structure is always like this. We have an agent or a mashup controller that sends input interactions to input devices and to get input payloads, and uses these payloads to calculate which output payloads it has to send to specific output devices. So using this atomic mashup abstraction, we can go from a mashup with this complexity to a mashup with this complexity, in which we have designated input devices that send inputs to the mashup controller, and the mashup controller can use these inputs to calculate which outputs it has to send to the output devices. However, to be able to have an exhaustive view of all possibilities is very daunting and very arduous, so we proposed our method, A-Mage, which takes TDs as its input, and using some templates and filters defined by a human agent is able to generate atomic mashups and then show them to the human agent in a graphical way, so he can select one or multiple of them and then generate the system description and runnable code out of these mashups. So to be able to see why we chose the atomic mashup abstraction, we have a look at the design space in general, and then the design space using the atomic mashup abstraction. So in general, if we have a set of n interactions in our pool, and we want a mashup with a length of k, our design space is the permutations of all these interactions given the length of k, and can be calculated using this formula. However, in the atomic mashup scenario, we simplified by splitting this pool into input interactions and output interactions. And given the desired mashup length, with the input length of Ln and output length of Lout, the design space can be calculated using this formula. So to show a comparison, we have a case in which we have 10 interactions, 5 of them are input interactions, 5 of them are output interactions, and we want a mashup with the length of 4, in which 2 interactions are inputs and 2 interactions are outputs. In the case of no abstraction, we get over 5,000 mashups. In the case of the atomic mashup abstraction, we get only 100. And this is approximately 98% reduction in the design space. If we have even more interactions in our pool and we want the same mashup length, the design space explodes and we get over 2 million without the abstractions, but only 36,000 with the abstractions, and that is also approximately 98% reduction in the design space. However, this number is infeasible to manually explore, so we need something else that can also constrain the design space that is generated even further. So we use filters and constraints, and this is the set of all filters and constraints we use in our methodology. However, I will not go over them here. I will show a demonstration of how our methodology works. We have implemented our methodology into WoT. It's a program that allows the handling of TDs. So you can have a look here. So this is a mashup, and these are all the devices that are in the mashup. And we can designate which devices are considered as inputs, for example these, and which are considered as outputs, for example these. And we can also specify which can be inputs or outputs. We can designate how many input interactions we want in our mashup, how many output interactions we want in our mashup. We can choose templates which define what type of input interactions we use. For example, we start with a subscribe or a read property or an action invoke. We can, for example, also filter using semantic annotations. For example, we can filter whole TDs, or we can filter based on interaction level semantic annotations. For example, only don't want any off commands, and we can also have restrict single interactions, very fine restrictions, and then we can generate TDs. For example, we generated 14 out of 60 possible mashups, and then we can generate for this selected one a system description here, which, as you can see, and code, which can be seen here. So now for our evaluation, we evaluate the execution time of our method given how many interactions we have. So as we can see, for a small number, for small mashups, and for a small number of interactions, our method is in bounds, so it executes in under a second, and therefore is in our intended scope. Our methodology is quite fast. We also evaluate the filtering power of different filters and constraints, and what we found is there are no specific strategies that can work with all scenarios, because there are good strategies for homogeneous scenarios where there are many devices that are the same, and better strategies in heterogeneous scenarios when you have every device is very different from each other. So to summarize and conclude, the motivation behind our paper was that it's infeasible to explore the design space of a whole mashup. So we try to divide and conquer this problem by using the atomic mashup abstraction. But what we found is that this abstraction alone is not enough. So we use filters and constraints to reduce the design space even further, to be able to generate a small amount of mashups that can be explored manually. And In our evaluation, we found out that the execution time of our methodology is smaller than 1 second in our intended scope, so it allows for multiple generation iterations to allow the fine-tunement of the filters and so on. And what we also found is that there's no definitive strategy that can work with all scenarios, and different filters react differently in different scenarios. So thank you, and I hope this was informative.